recorded.
This week's presentation is given by Eric Booth from the Department of Agronomy and Department of Civil and Environmental Engineering. He's currently at the University of Wisconsin, Madison, I believe that's correct, developing a framework to assess the water quality and quantity impacts of climate change, shifting land use, and urbanization in a Midwestern agricultural landscape. I look forward to hearing about this. The other important component, I think, if we could ask Eric before he begins, is to just give us a brief summary of the NSF Water Sustainability and Climate Program that has gotten off to a very successful start.
Yeah, absolutely. Great. Well, thanks a lot, Todd, for the introduction, and thanks everyone for coming online for today's webinar. It's an honor for me to be addressing the Quasi community and telling you a little bit about our project that just got underway just this last April. So as Todd mentioned, it is looking at both quality and quantity impacts of climate change, land use change, urbanization in the Yahara River watershed. And you see some pictures here on this first slide of the key aspects of the watershed. So this is where the city of Madison is located, so the seat of the state government, the home of the university. But as you see on the bottom too, we also have agricultural landscape dominating the system, and a very wet landscape, but also a landscape that we are very proud of our water resources, and we do a lot to protect these water resources. And there's definitely a lot of issues that we're contending with in trying to maintain a sustainable water system. So let me just give you an outline of what I'm going to be talking about today. I'll give you a brief overview of the Water Sustainability and Climate NSF solicitation, as Todd mentioned. And then I'll give more of a brief background on the Yahara River watershed as a whole, starting with just basic physical setting of the system, a little bit of history of the issues, and then all the way up into today, what some of the current issues are that we're going to be addressing. And then I'll spend some time talking about the project itself and some of the key elements of our research effort. So first off, the Water Sustainability and Climate solicitation. The first call came in 2010, and that's the one that we're a part of. And it's a multi-directorate solicitation involving directorates of engineering, geosciences, biology, social, behavioral, and economic sciences. So a really interdisciplinary solicitation. And it's trying to address this challenge of ensuring an adequate supply of both quality and quantity of water in the face of increasing human needs and climate change, and trying to address some major gaps in our understanding. But the main goal being understanding and predicting the interactions between water system, climate change, and land use, the built environment, and maintaining ecosystem function and services through this idea of place-based research and creative models. And there are two separate categories that are under the Water Sustainability and Climate heading. So category one is looking at small exploratory or incubation grants. So these are 1 to 2 years, up to $150,000. And 10 of those were funded in the 2010 call. And category two is more of the place-based observational and modeling studies, and that's what we are a part of. And those are up to 5 years of funding and $5 million. And then finally there's category three, which is more the synthesis, modeling, and integration grants that are using existing data. And those are 3 to 5 years and up to $1.5 million. So that's just a brief background on what WSC is from NSF. And then this is who we are. This is Water Sustainability and Climate in the Yahara River watershed. And let me just give you a brief background of some of the PIs. There's 6 of them. And Chris Kucharek is the lead PI. He is in the Department of Agronomy as well, and has kind of a climate science background, and now merging more towards agroecology. And Steve Lohide is in the Department of Civil and Environmental Engineering and has more of a background in hydrology, hydroecology, and services. And then Monica Turner is in the Department of Zoology and has really been a leader throughout her career in the field of landscape ecology and kind of spatial variability of ecosystem services. Steve Carpenter is another well-known researcher in the field of limnology and water resources in general, and he'll be looking at both lake water quality modeling, but also some of the social science aspects of the project, as he's very interested in ideas of resilience and sustainability and scenario analysis, which I'll talk about more. And then Adina Rissman in the Department of Forest, Wildlife, and Ecology is on the social science part of the project and looking at more of making, environmental decision-making, and policy. And then finally, Corinna Grease in the Center for Limnology is our data manager, which is a very important aspect of the project. We've got a lot of different data types to keep track of, not only our own, but others' data that we're trying to integrate into the project. So there's about 20 of us total, and I won't go through everybody's name, but I am one of 2 research specialists, and I'm kind of in charge of wrangling everybody together and trying to make sense of all these different threads being woven together. So a little bit of a background on the watershed itself. So we're in southern Wisconsin. I apologize, the picture in the upper right is a little small, but you'll see that we are kind of right at the edge of the upper Mississippi River basin down in southern Wisconsin. And the Ohio River watershed is mostly in Dane County in the southern part of the state, and it drains about 1,300 square kilometers. It contains 5 major lakes that have been significantly impacted by changes in seasonal climate, agricultural land use, and a growing urban environment. The watershed's physiography is really strongly influenced by glaciation, so that occurred as recently as 14,000 years ago, and it's an area where deep glacial deposits dammed up really a large pre-glacial valley, forming a chain of large lakes, and those are our prized assets of the region, we like to think. And it also led to a relatively flat, poorly drained landscape characterized by these various glacial deposits. Paleozoic bedrock is generally covered by up to 100 meters of this material, mostly till material of varying soil types, gravel, clay, silty sand, a hodgepodge of everything. Land use is largely agricultural, as you can see from the image in the center. Both the northern and southern parts of the basin are definitely dominated by agriculture, with an urban center right in the center of the watershed, that being the Madison metropolitan area. But for the most part, it's dominated by agriculture, and that's principally corn, soybean, and dairy. So dairy production really dominates farming in the watershed, and that, from a land use perspective, means forage crops of corn for silage, alfalfa, grasses, and soybeans even. And then it also means manure. So the manure is produced and typically is used as a source of nutrients and organic matter for local fields. And there's also some beef cattle in the watershed, and then some corn and soybeans just for the global market. And as I mentioned before, Madison is the seat of the state government and home to the university. The state government's the largest employer. We also have health services, retail, some manufacturing. And we think it's a pretty strong local economy that also feeds back into kind of local agriculture, as we've seen an increasing direct-to-market sales. We've got one of the largest farmers markets in the nation, and there's been a lot of programs to connect local growers to local institutions, such as the university. But from a land use perspective, that's a really small component, but a growing one. Open space is also very important. We've got lots of parks in the Madison area, conservation areas, wetlands. Recreational use of the water resources is, popular for fishing, sailing on the lakes, boating, water skiing. But there's also efforts to kind of manage and restore some trout streams in the area. But overall, it's a mix of urban, croplands, wetlands, and some kind of natural prairie forest type environments. here's a little bit of hydrologic background. Here in the upper left, there's mean monthly precipitation and stream flow at the outlet. And you'll notice a little bit of seasonal variation in precipitation, where we get most of our precip in the spring, summer months. But you'll notice that mean monthly stream flow is a little bit different, so that's a signal dominated by snowmelt in the early spring, late winter. But it should be noted that lots of variability in the timing of peak flows occurs. About half of our peak flows don't come in that late winter, early spring period. So these are going to be convective thunderstorms in the summer that do have a big influence on the system. So you can see on the lower left an example of a typical year, maybe a little bit heavier snowmelt than normal, but for 4 different gauges. So I should mention that the USGS has a lot of different gauges in the watershed that have really nice records that we are definitely taking advantage of. And these are just 4 of them, the big ones. So from top to bottom, we've got the Upper Yahara in blue, the Pheasant Branch Creek in green, and you can see they're a little flashier. And then at the very bottom, we have the outlet showing some big events in the snowmelt period. But bed gauge is just downstream of the lakes, and you'll notice kind of that mediating effect of the lakes. So that's kind of the big take-home point of this slide, the influence of the lakes. And also, as a consequence of glaciation, as I mentioned, it's a pretty flat landscape. And you can see this just by, these are some of the local slopes in the watershed. And then if we go even a little bit further, and these slopes actually suggest there are also some internally drained basins. So this is a pretty complex issue that we're trying to get a handle on. Mapping these out is not a trivial exercise, because you have a lot of different issues related to whether a road has a culvert underneath it or not. But this has a huge impact on how surface hydrology functions in this watershed. So just a little bit of background. And then if we look at the hydric soil rating of the watershed, we'll notice a lot of hydric soils. And this is also a consequence of this poorly drained landscape. And all these hydric areas are not wetlands today. A lot of them have been drained, which gets me to my next slide. So here's just a really quick and dirty history, 200-year history of the watershed. And you'll notice on the bottom left some pre-settlement vegetation estimates. So mostly an oak savanna, prairie, wetland type landscape, and now transitioning to what we have today in the figure immediately next to it. And Madison was founded in the late 1830s, and almost immediately water level regulation on the lakes started to occur, mostly for hydroelectric power, or for mills, I should say, not hydroelectric. Not quite yet, but this transitioned into a big boom in the city, and an extensive transition of the land use pattern from this prairie savanna wetland mosaic to a watershed dominated by agriculture. And from a water quality perspective, we really start to see some of these cyanobacteria blooms start to occur in the late 19th century and are still a problem today. But back in the late 20th century, the real big issue here was raw sewage directed to. So this is an issue that a lot of big metropolitan areas grappled with throughout this the 20th, 19th century. But Madison in particular was pretty heavy hit just because of this idea that the landscape was so poorly drained that sewage just really didn't go anywhere once it went into the lakes. And so Madison was kind of, as a consequence, at the forefront of wastewater treatment technology, and developed a lot of the treatment technologies that we see across the country and the world today. So we fixed that sewage problem ultimately, though, by diverting our treated sewage around the lakes and down into the Badfish Creek watershed, which I'll show in more detail here in a second. But right as we were trying to figure out that problem, the issue of non-point source pollution really started to creep out. So if we look at agricultural land use history in the basin, we've got wheat dominating in the late 20th century, but then moving more towards dairy, and that's what we're really known for now in the watershed. And then, as you know, most agricultural watersheds, the history of them, see mechanization coming into the history in the mid-20th century, and corn and soybeans becoming quite dominant. And also, on top of that, an increase of intensive fertilizer use. So that's the ag story. The urban story, we really start to see a big increase in urbanization in the mid-20th century after World War II. This also led to increased groundwater pumping, and I'll talk a little bit more about those here in a second. But then on top of all of this, we've got some climate trends, looking at increasing rainfall over the last 50 years. And again, I'll get to that in a second. But this is just kind of a broad overview of the whole history, and I'll talk a little bit more about the current issues here in a second. But one more thing to point out, this watershed really has been looked at for well over 100 years from a research standpoint. It really helps to have the university on the shores of Lake Mendota, and this is really where the science of limnology began. And so we really have a lot of shoulders to stand on as we go forward on this project. So a little bit more about some current issues. So nutrient enrichment of not only the lakes and streams, but also groundwater in the form of nitrate issues are really some of the bigger problems that we are faced with. And so these come from non-point sources, of course, manure being a big one, but also fertilizer and some urban sources. But we know this leads to algal blooms, eutrophication issues, public health. And if we look at this figure on the lower right, this is phosphorus, and phosphorus being what we're really been most interested in from a research and management standpoint, but there also is some recent evidence that suggests that nitrogen is also has a potential to be a limiting nutrient for algal growth. But here's phosphorus load to the lakes, and showing even under pretty intensive management efforts over the last decade or so, we really haven't seen much of a decrease. And that's not really saying that we're not trying, we're not doing well. There has been some very intense precipitation events that have occurred over the last 10 to 15 years that have made it pretty challenging to reduce these loads. And so here are some of the usual suspects in terms of non-point source pollution, as I mentioned. So manure is a big issue and increasingly becoming an important issue with the kind of concentration of dairy cows across the basin, what we do with the manure, but also fertilizer, cropland erosion is certainly an issue. And once we get into the urban areas, new development can definitely be a source of these of nutrients and sediments. So moving more towards water quantity issues, I'm going to talk a little bit about each of these issues: increased precipitation, increased urbanization, and increased groundwater pumping, and they're kind of the main drivers of what's going on recently. So here's increased precipitation, and since the 1930s, and you'll notice the next few slides I'm going to show kind of this time frame of 1930 to 2010. And we can see a pretty strong increase in mean annual precipitation from the 1930s to today. But so that's on a mean annual basis, but even if we just look at on an event basis, this is even more interesting, we think, that some of these really big rainfall events, so these are 50, 75 millimeter per day events, and the frequency of these events have really increased over the last 2 decades, and as one of our predictions for future climate change, these are slated to go even higher. So that's precipitation. On top of this, we've had this urbanization signal, as I mentioned before. The population of Dane County has been steadily increasing throughout the 20th century, and residential development has been occurring on lands previously used for agriculture. And the Wisconsin Department of Administration estimates that the Madison metropolitan area will add over 100,000 people in the next 20 years. So that's about an 18% increase. Then associated with urbanization, we've got increased groundwater pumping, another common issue in urban areas. So on the left, you'll see the graph of groundwater withdrawals through time. And then another interesting issue here, I mentioned this idea of sewage diversion. So the map on the right is showing in the blue circles all the different municipal wells in the watershed. And essentially what's happening is water is being taken from a deep sandstone aquifer where we get our water supply, brought to all of the users, and then shipped to a wastewater treatment plant right at that point. And then that effluent is shipped over the basin divide and into the Badfish Creek watershed down in the southern part of the Yahara Basin. So all of this area downstream of Madison is kind of suffering from this loss of base flow as a consequence. So it was a great fix in terms of improving water quality to some of these lakes that previously got wastewater discharge, treated wastewater, but still had a lot of nutrients in them. But this has a big implication for kind of flow, base flow, but also flow to wetlands, and it just suggests this effect of groundwater pumping. And on top of this, not explicitly related to specific water quantity changes, but in the background, we've definitely seen a lot of signs of warming in the Yahara watershed. And one of the biggest signs has been this really long-term record of ice-on and ice-off dates from Lake Mendota, going back all the way to the 1850s. And we've seen some of the shortest ice duration years occurring in the last several decades, and we can definitely add this year's scenario to that. I don't remember exactly the duration off the top of my head, but it's definitely below that trend line. So that's one indicator, but we've also seen, we like to say, we have this Wisconsin Initiative on Climate Change Impacts that finished their report a few years ago, and we like to say it hasn't become warmer, it's just become less cold. So that means nighttime low temperatures have significantly increased, but daytime highs really haven't shown the same amount of increase. But we've also seen significant decreases in the number of days below 0 degrees Fahrenheit. So I'm sorry about switching units, but we've seen 20 days less, 20 fewer days of below 0 degree conditions since 1976. And another indicator is the growing season length has increased by almost 2 weeks since 1976. So definitely a warming signal that we can't really tease or see necessarily in the hydrologic record, but going forward definitely is something to keep in mind. So some of the hydrologic consequences of these changes are shown here, and I'll go into detail on each one of these briefly. So first off, as you might imagine, this could cause some issues and increased lake flooding. So this is showing Lake Mendota maximum annual stage over the last 70-plus years, and we've seen a significant trend in that maximum annual stage. So you might think this might be just a precipitation signal purely, but a way of teasing this out from the two drivers that could affect this, so urbanization and precip. This is an analysis showing kind of the estimated response of a given rainfall event on Lake Mendota stage. So this is taking on a decade basis several storm events and then creating a regression relationship. So it's kind of a rough estimate of this response. So a regression between storm rainfall and the lake stage response that corresponds with that rainfall. And you'll see a very significant or substantial increase throughout the record. And this is showing the upper and lower 95% confidence limits. So it's kind of a nice way just to illustrate that this just isn't precip alone that's increasing our flooding issue on the lakes. There's something going on with land use, and that something is a strong increase in urbanization. And we also see this not just in the lakes, but in the streams as well. So the upper graph is showing one of the more urbanizing basins in the Yahara watershed. And even though the trend is not significant, it's a pretty short record, you do see significantly more variability over the last couple decades, while this basin is really urbanized significantly. And then down below the first three lakes, we also see this peak annual stream flow trend, and that is significant as well. But that is kind of showing both the influence and the merging of the mean annual precip trend and also the trend in the frequency of these high rainfall events. Another interesting issue that we're trying to get a little bit more attention to is this issue of internally drained basins. I mentioned it before, but here's an example of an urbanizing watershed opening up a previously internally draining basin. And so this is a double mass curve showing cumulative precip on the x-axis and cumulative stream flow on the y. And you can see in 1993 a pretty sharp divergence from that relationship, showing an increase in stream flow without associated increase in precip. And that, from just the history of development of that area, shows it corresponds with some significant development in those intervening years. So it's something to definitely be concerned about from a flooding perspective if you're interested in the lakes. We've also seen, so this is more of a signal of precipitation. These are in more of the rural areas that we've seen some increase in groundwater flooding, so persistent surface water features that are connected to the water table. And we've seen these increasing in extent over the last decade or two. And I know this is a pretty short record to show this, but we don't have a ton of long-term groundwater monitoring well data. But this is also showing just some aerial photos of this rising water table in some areas of the watershed that's really been impacting some of the corn growers. And a lot of land has been going out of production as a consequence. We've also seen, related to groundwater pumping, more variable base flows. So this is showing flow at this point in the watershed, just below the third lake here. And you can notice in the record, this is, 7-day low flows for each year of the record. And once that diversion occurred, again, that sewage diversion, you can really start to see some of these lower flows decreasing. And that's been pretty obscured in the last few years. We've seen some heavy rainfall, or some increases in mean annual rainfall. But it's something to keep in mind as we go forward, that we could definitely get these low flows again once we start seeing some drier conditions. And here's just another figure illustrating the effect of groundwater pumping on the water table. This is from some modeling by the State Geological Survey and the U.S. Geological Survey that's really been doing a lot of great work in the basin for several decades. But this is showing drawdown of the water table, simulated drawdown around up to 50 or 60 feet in certain parts of the metropolitan area. And we definitely have associated issues with reduced base flow and reduced flow to wetlands. So finally, we do have some other watershed issues that might not fit purely into water quality and quantity, but definitely impact land use. We've seen a loss of agricultural land, and that definitely has social ramifications and the relationship with urban development pressures. But we've also seen increasing demand for biofuels, and that's something I'll talk a little bit more about here in a second. But it's an interesting basin to look at because it is so dominated by agriculture, and we have this urbanizing element too. But as this water, energy, food nexus starts to become more and more of a focus, this is a watershed in particular that could change quite a bit. So getting on to our project finally. Our central question here is, how will ecosystem services vary and how can they be sustained in the Ohio River watershed as climate, land use, and the built environment and human demands change in the future? And some of our other research questions are looking at kind of resilience as this main guiding concept. And so how can different regional governance systems be made more resilient and adaptive? And also just figuring out in what ways are these regional human environment systems resilient, and in what ways are they vulnerable to potential changes that come in the future. So our four elements of the research are modeling, field studies, regional governance evaluation, and integrated scenarios. I'll go into a little bit more detail on each one of those. So again, here's just all 20 of the staff here at Water Sustainability and Climate. And we are broken up into these kind of four different elements, but I'm kind of charged with integrating all this together and making sense out of it. But I'd also want to note that we're really leveraging off of some other efforts that are currently underway, both the North Temperate Lakes LTER and also the Great Lakes Bioenergy Research Center, and even agricultural research at the UW in the basin has been going on for many years. And so we're really standing on the shoulders of a lot of researchers that have been looking at basin issues for quite a while, and we're very fortunate to be working with them. So our first kind of guiding concept here is to quantify ecosystem services in the future. And so this is a lot going on here at this table, but just focus here on the different ecosystem services. So some of the common ones related to hydrologic services like freshwater supply, surface water quality, and groundwater quality, but also getting at crop production, which is super important in this watershed, as I've mentioned. And then some of the regulating services, such as flood regulation and climate regulation, so carbon sequestration, but also getting into more issues related to lake recreation and how that's impacted by the occurrence of algal blooms. And so you can start to see some of these ecosystem services would benefit from some kind of predictive tool and model simulation. So that's where our modeling effort comes in, and I know there's a lot going on in this slide as well, but let me just walk you through it here real quick. We've got a couple of different components here that we're integrating together. So agro-IBIS, that's this structure here on the upper left, is kind of the main engine, and this is a model that Chris Kucharik has done a lot of work developing and testing within the Midwest specifically. And it's a model that simulates energy, water, carbon, and nitrogen, the balance of the soil, vegetation, atmosphere system. And it simulates natural vegetation. It also simulates agro-ecosystems like corn, soybean, wheat, and it accounts for different management practices and the effects of environmental stressors on crop development and things like that. It's a pixel-based, one-dimensional vertical model, which is then also linked with THUM, so that's a terrestrial hydrology and biogeochemistry model that routes surface runoff and subsurface drainage through a stream network that can include lakes and wetlands and reservoirs, and it takes into account the physical morphology of the basin. And then we are going to be linking that with a lake water quality model, and this has been from research by Steve Carpenter and others looking at kind of lake water quality on an annual basis using inputs of phosphorus load and generating kind of the probability of a algal bloom on a given day in the summertime. So that's kind of the framework we're starting with, but we're going to be making some model innovations, and one of the big ones here is adding a groundwater flow module to AgroIBIS. And here we're going to be using ModFlow, and this is, again, we've got the good fortune of using a model that the U.S. Geological Survey and the State Geological Survey is currently wrapping up this year, looking at the entire regional groundwater flow system, and it's a really sophisticated model, big improvement since the last time they did this a couple of decades, or about 10 years ago. And so we're going to be using that and integrating that into AgroIBIS, and so we can have a coupled hydrologic surface water groundwater model. And so that's one key element, and as I mentioned before, groundwater is definitely a key component to get right in this watershed because it is really interacting with the surface quite a bit. The second model innovation is AgroIBIS is accounting for nitrogen but not phosphorus, and we really are interested in getting estimates of phosphorus yield and transport to the lakes. And so we're going to add in that component into the modeling, as well as AgroIBIS, as its namesake suggests, is much more dealing with agricultural, rural type land uses, but the urban component is something that needs to be better parameterized, and we've got a student working on exactly that issue, trying to start from a small scale, looking at how water is used on kind of a residential lot, but then trying to scale that up to a larger sub-basin scale so we can work with it within AgroIBIS. And then finally, we want to include key bioenergy crops into AgroIBIS. So this is crops like switchgrass and miscanthus that are going to be potentially big players in the watershed in the future. And on the heels of that, this is what I'm talking about as far as future watershed bioenergy landscapes. So replacement of annual monocultures to these perennial monocultures or polycultures is something that has gotten a lot of attention. And so we're interested in modeling these types of systems as we go moving towards the future. And we are very lucky to have the Great Lakes Bioenergy Research Center doing research within the basin itself. And that's happening up in the upper part of the basin. Up here is where the Arlington Agricultural Research Station is. But we're also going to be adding in quite a few monitoring stations. We already have added in these monitoring stations last season. So we're looking at different land cover types and how they process water and nutrients. And so we've got 3 forest sites, 3 grassland sites, 3 wetland sites, 3 urban kind of turf grass sites, and then the agricultural sites at Arlington, plus a working farm that has been impacted by this issue of groundwater flooding that we're going to kind of zoom in on here in the upper basin. And so at each one of these locations, we are looking at soil moisture, soil temperature, weather, groundwater levels, but also periodic measurements of stomatal conductance, leaf area index, and adding to that some remotely sensed data. So we have cameras, thermal cameras, a near-infrared camera that we can put onto a Cessna and actually get up and fly fairly low to some of these sites and get some really high-resolution, remotely sensed data. And with those, we're kind of interested in plant health and potentially mapping out evapotranspiration. So the idea here with the stomatal response is a very small change in evapotranspiration here. So these are just normal numbers for a given year in our region, but a very small, like, change of 5% in evapotranspiration that could be associated with a land use change could translate into big changes in other parts of the water cycle. say, if it changes recharge by 20%. So there's a big, strong lever that evapotranspiration can play in this watershed that we really want to try and get a better handle on. Along with this field effort, we are also looking at the urban heat island in a little bit more detail. So there's a PhD student working specifically on this aspect of the project, trying to set up a network of relative humidity and temperature sensors across the Madison metropolitan area, and really trying to figure out how does urban development affect energy and water flux in the watershed. And that will definitely feed back into our modeling. And we haven't really been able to tease out that signal as far as hydrology is concerned, this urban heat island effect. But as we get further and further into the 21st century, we might see that as a pretty strong issue. So this is the third aspect of the project. It's something I'm a little bit less familiar with just because of my background, but I'll give you a little bit of a synopsis of what's going on. So the social scientists on the project are trying to evaluate regional governance, and this is a figure kind of showing one of their institutional networks and how they try and figure out how things are connected. This is at the county level here. And really interested in this question of how these different governance systems are organized and how they manage these water and land-based ecosystem services, and what kind of strategies they are deploying to intervene to enhance ecosystem services. And looking at a bunch of different scales of this question, both from the kind of the system perspective and all the way down to individual user decisions, so using surveys and those kinds of techniques to look at that question. But also very interested in the role of science in how ecosystems are managed and how decisions are made, both kind of a retrospective analysis and also then linking into how that might flesh out in the future. But then the final kind of element of the project is this idea of integrated scenarios. And this might be something that some people are familiar with in terms of the special report on emission scenarios of the IPCC or the Millennium Ecosystem Assessment. And so scenario planning is this method for kind of thinking creatively and systematically about complex futures. And the idea here is we're trying to develop 4 contrasting and plausible scenarios of the future. And these are going to be designed by a diverse set of stakeholders through workshops that we've already had 3 of them. And then we're going to be linking those kind of storylines with our model simulations so that we can kind of enrich these scenarios and actually quantify ecosystem services under each of the scenarios. And so I know I'm running a little over time, but this is kind of an example of how these scenarios are generated. We're trying to get people to think about drivers outside the region and different wildcards. Say, for instance, we might have migration into the area. Maybe sea level rise occurs faster than expected, and we might see more influx into the Midwest, or disease epidemics. So these big wildcards that people don't normally think about are a little bit outside of our normal 5-year kind of political window that we are spending a lot of time thinking about here in the state of Wisconsin especially. But then also thinking about some regional processes and how institutions are going to adapt to different regional drivers and how policies are going to then be formulated as a consequence. But ultimately, getting to these outcomes, which are then going to be linked up with this model of simulating ecosystem services. So we ultimately generate these kind of enriched storylines that can hopefully help people make better decisions going forward. And so that's kind of the goal of these scenario development exercises, is to expand basic knowledge, kind of provide an arena for conversation about the future, find new and exciting ways of influencing the future, but help guide decision makers towards a more sustainable and resilient future. And kind of the timeline here is to develop these. We've already had 55 interviews, 3 workshops, and we're kind of developing initial storylines this year as we are kind of refining our modeling techniques. And next year we'll then start to have the modelers come together with these scenarios and make sure that we can model what are actually coming up in these scenarios, and also just to try and see how diverse and disparate these scenarios are going to be, because we don't all want the same scenario. We want pretty contrasting scenarios so we can get a nice full picture of what are the potential futures ahead. But then as we get into 2014 and 2015, we will be doing a lot more outreach and getting these scenario storylines out into the public and getting feedback on them. So there's going to be a big outreach effort that's already starting to occur with these workshops, but once we get these scenarios going, that's going to be even more of our focus. So in summary, we're developing this scientific framework to guide decision-making towards more sustainable use of water resources through this modeling, monitoring effort, and also looking at regional governance evaluation, but all under this big umbrella of integrated scenarios. And some of the key elements are very interdisciplinary effort and a lot of stakeholder participation, sophisticated modeling, and a big outreach and education effort. So with that, I'll just show some acknowledgements. Of course, the National Science Foundation and a lot of UW-Madison colleagues, USGS, various regional partners that have been helpful so far and will continue to be as we move forward. And I invite anyone to take a look at our website, too, for updates as we move forward. So thanks. I'd be happy to take any questions.
Well, thank you, Eric Booth from University of Wisconsin. Do we have questions from the floor? If I could start, maybe if one could supply a question through the chat box if you'd like, or just ask the question directly through the telephone. Question I had was, in much of that part of the Midwest, they have tile draining system for shallow groundwater drainage. Is that an issue in your watershed?
Yeah, that's a great question, and something that has definitely been a difficult thing to monitor. There's been a lot of research done through some of the ag research stations. So Discovery Farms is one of them. It's a University of Wisconsin Extension program. And yeah, I mean, it's very difficult to map these. There's probably ways you could do some kind of lumped parameterization to try and get them into the models. But yeah, without being able to map them very well, it becomes a pretty difficult problem to kind of simulate at that scale. So there's got to be ways to get around that and try and account for that kind of as you scale up to maybe a sub-basin scale. But it definitely does occur in these areas, these wet areas in particular. And I think it's something people are becoming even more interested in some parts of the watershed. Been dealing with these groundwater flooding issues. If there's ways that they can get that water out, that would be great as far as their crop development goes.
I guess my question related to that would be nutrients in the tile drains. Is that
right? Yeah, absolutely. And in particular, nitrate for sure is that's going to be a very important conduit for how that gets into the stream network and has big implications for denitrification or lack thereof. Yeah, it'll be a challenge, and I don't know if we have a definite solution for how we're going to be handling it, but it's definitely on our radar.
I have a question. This is Ferdy Helviger from Northeastern.
Hello.
Hello. I noticed you're planning on making these futurecast predictions for these various scenarios, and so you're going to be using your model to make predictions on a long time scale. of decades or longer.
Mm-hmm.
And I was wondering if you're planning on how you're planning on validating your predictive ability or the predictive ability of your model at that time scale.
Sure. So yeah, let me first say that I think prediction, I hope I didn't use that term, but these aren't necessarily predictions of the future. They specifically aren't. I mean, we're just trying to get at different scenarios of the future, so we're not trying to predict the actual outcome of this watershed. We're just trying to kind of use scenarios as a tool to see what are potential scenarios of the future and how those different scenarios would then affect services. But as far as model kind of validation, and we're going to be calibrating to 2011 and 2012, where we have our most extensive field data sets. But there also is data that goes back several decades in terms of stream flow and water quality data that we would be able to use in terms of model validation. So we can only use what data is available in terms of model validation, but it will be very important in terms of really trusting the ability of our model to simulate reality. But just wanted to make clear that we're not necessarily predicting the future like a climate model would, for instance, but we're trying to just simulate ecosystem services under different scenarios. I know it's kind of a nuanced point, but yeah. Does that answer your question?
Yes, thank you.
Thanks.
Kongcheng Wu had a question. So many factors are included in your work, but what are some dominant processes to affect regional hydrology?
Sure. So, let's see. Definitely dominant processes are getting precipitation right. So in terms of model validation, we're going to be spending a lot of time gathering up rainfall data sets, so using NexRad data, for instance, to really get at spatially distributed rainfall, because we definitely have seen in previous events that there's quite a bit of variability around the watershed. But that's kind of an issue that's important in a lot of places. So more specific to Yahara, I think the big dominant processes will be this transition from urbanization or from agricultural land to more urban type landscapes, and making sure that we are able to simulate that transition quite well. These urban, very managed systems it can be pretty challenging to model, but they include potential infiltration practices. It's things that are going to be challenging to scale up to kind of a sub-basin scale. So, but have absolutely enormous implications for how hydrology occurs. So, I would say those are kind of the dominant processes that we're, and I guess surface water groundwater interaction too is a key component.
Yaqub Rahim has a comment. Thank you for a great talk. I am curious if you are considering looking at developing historic land use maps using Landsat to see how historic land use changes have affected hydrology and thus aid in understanding how future land use changes will affect hydrology.
Yeah, absolutely. There's been some work previously. There was a master's student, I think, 10 years ago or so, that did not Landsat, just looking at aerial photos and kind of reconstructing historic land use. So, depending on how our model validation is structured, we're definitely going to have to use some of that historic land use data in order to get our model inputs correct. So, that's a great suggestion, looking at Landsat data to get at a little bit better resolution maybe of land use. So that's definitely a component that we're interested in looking at. Thanks.
Thomas Walsh had raised his hand at one point. Are you still?
No, I'm good, thank you.
I guess my question in terms of snow and ice impacts, I mean, that affects winter wheat production. Would that be correct? I'm not from up there, but.
Yeah. So in terms of runoff too, that's a big concern up here is the effect of frozen ground on spring or early spring runoff events, and that definitely has implications for manure management. Some of our bigger kind of water quality issues in the last decade or so have been these runoff events on frozen ground right after manure has been spread. So yeah, getting a handle on soil temperature and being able to simulate that correctly is going to be really important, both from a water quality and quantity perspective, because those early spring snowmelt events definitely can cause flooding issues downstream on the lakes. So yeah, that's going to be a big component.
Do you see any deposition effects? Sometimes there's dry deposition during the winter that accumulates acids in the snowpack. And have you seen anything like that in your area?
No, not specifically, but yeah, I'm sure some colleagues here in the Department of Agronomy, if that has been happening, have been seeing it. But I'm relatively new to the department here. I come from civil engineering, so I'm getting up to speed with agronomy as quick as I can. But I personally have not seen that.
We're reaching the end of our session. Are there any other questions? Well, thank you all for attending, and thank you, Eric, for spending the time with us. This was great. I really enjoyed it.